Good morning, everyone. We are the Group 7, and we are going to discuss about the light absorbed as photons, the photoelectric effect. So our main objectives for today is to explain the physical characteristics of photoelectric effect, explain why the photoelectric effect cannot be explained by classical physics, and identify real-world application of the photoelectric effect. So what is photoelectric effect? When a metal surface is exposed to a monochromatic electromagnetic wave with a short wavelength or high frequency, it absorbs the radiation and emits electrons from the surface. And this discovered in 1887 by a German physicist, Heinrich Rudolf Hertz. Later on, Albert Einstein's photon theory explained the effect of this in 1905. We have a photoelectric experimental setup here. So we have two electrodes, which is the cathode and the anode. The yellow object here serves as our target material or the anode, and the gray object is the cathode. So when an incident light reflects to the anode, its electron flow to the cathode. So photocurrent, it is a current that flows when a photoelectrode is illuminated. And stopping potential, it is the potential difference at which the photocurrent stops flowing. There are three characteristics of photoelectric effect. First is the absence of lag time. It refers to the immediate emission of electrons when radiation strikes a target material without any delay. Second is the intensity of incident radiation and kinetic energy of photoelectrons. So in our first graph, the detected photocurrent plotted versus the applied potential difference shows that for any intensity of incident radiation, whether the intensity is high or lower, the value of the stopping potential is always the same. The third one is the presence of cutoff frequency. It states that for any metal surface, there exists a minimum frequency of incident radiation. And we have another graph here. It emphasizes that kinetic energy of photoelectrons at the surface versus the frequency of incident radiation. The photoelectric effect can only occur above cutoff frequency or the FC. Measurements for all metal surface give linear plots with one slope, and each metal surface has its own cutoff frequency.
So these are the effect of the frequency of the incident light on the kinetic energy of the photoelectron. So as you can see in the picture, the photoelectric effect does not occur when red light strikes the metallic surface because the frequency of red light is lower than the threshold frequency of the metal. The threshold frequency is the minimum frequency of light required to provide enough energy to overcome the work function of the metal and emit photoelectrons. Below this frequency, the energy of the photon is insufficient to release electrons. The photoelectric effect occurs when the green light strikes the metal because the frequency of green light is above the threshold frequency. When light of sufficient frequency strikes the metal, it provides enough energy to eject electrons. These emitted electrons are called photoelectrons. The photoelectric effect also occurs when blue light strikes the metallic surface. But the emitted photoelectrons have a higher kinetic energy compared to those emitted by green light. This is because blue light has a greater frequency than green light. Since the energy of the photon is higher, the photoelectrons that are emitted will have higher kinetic energy after overcoming the metal's work function. So the greater the frequency of the light, the higher the energy per photon, and thus the greater the kinetic energy of the emitted photoelectrons. So the equation for photoelectric effect is energy of a photon is equal to work function plus kinetic energy of the ejected electrons. So the first component is energy of a photon. It represents the energy carried by a single photon of light. It is directly proportional to the frequency of the light wave and can be calculated using the equation E equals h multiplied by B. Where h is Planck's constant, this equation shows that higher frequency light, such as blue, carries more energy per photon compared to lower frequency light, such as red. So the next component is the work function. The work function is the minimum amount of energy required to remove an electron from the surface of the metal. It is a characteristic property of the material. If the energy of the incoming photon is equal to or greater than the work function, the electron will be ejected. The work function is measured in joules. And lastly, the kinetic energy of the ejected electron. After a photon strikes the metal surface and ejects an electron, the remaining energy is converted into the kinetic energy of the emitted electron. This represents the electron's kinetic energy after emitting from the material. So the equation of kinetic energy of photoelectrons is Kmax is equal to Planck constant times frequency minus phi. The energy of the incoming photon is absorbed by the electron. Part of this energy is used to overcome the work function, and the remaining energy is converted into the kinetic energy of the ejected electron. So the equation of cutoff frequency is frequency cut is equal to pi over Planck's constant. The cutoff frequency is the minimum frequency of light required to emit an electron from the surface of a material. If the frequency of the incident light is below the cutoff frequency, no electrons will be ejected, regardless of the intensity of the light. This means the cutoff frequency is directly proportional to the work function. The higher the work function of a material, the higher the frequency needed to eject electrons. The cutoff wavelength is the wavelength corresponding to the cutoff frequency. It is the longest wavelength of light that can still cause the emission of photoelectrons from a material. So the cutoff wavelength is inversely related to the cutoff frequency, meaning that a higher cutoff frequency corresponds to a shorter cutoff wavelength. These relationships are central to understanding the photoelectric effect and how light interacts with matter, particularly in the context of the energy required to release electrons from a material surface.
Albert Einstein proposed that light is made up of protons and each proton carries a specific energy. By the equation of energy of protons is equal to Planck constant multiplied by the frequency of light. And this explanation of Einstein explained the photoelectric effect, where the light ejects electrons from the metal only if the frequency is high enough. So this idea of his contradicted to the classical wave theory, proving that light behaves both a wave and a particle, or what we call the wave-particle duality. So this idea of Einstein later on became the foundation of quantum mechanics that changed our understanding of light and matter. So we have the sample problem of photoelectric effect. So in a photoelectric effect experiment, the threshold wavelength of light is considered as 380 nanometer. If the wavelength of incident light is 200 nanometer, find the maximum kinetic energy of emitted electrons will be given as photoelectrons, or the E, also equivalent to 1237 divided by wavelength of light in a nanometer. So the given data is threshold wavelength of light is 380 nanometer and the wavelength of incident light is 260 nanometer. So since we are dealing with finding wavelength, we're going to use this equation. Maximum of kinetic energy is equal to Planck's constant multiplied by the speed of light divided by the wavelength of light. So we've converted the joules unit into electron volts, or EV, which result to 1237 electron volts, and it is multiplied by threshold wavelength, which is equal to 380 nanometer minus 260 nanometer. And it is also divided by 380 nanometer times or multiplied into 260 nanometer, which result to 1.5 electron volts. So therefore, the maximum kinetic energy of emitted electrons in photoelectric effect is 1.5 electron volts.
So let's move on to the application of the photoelectric effect. So there are some application of the photoelectric effect. First is the solar cells. Solar cells use the photoelectric effect to convert sunlight into electricity when light strikes a semiconductor material, for example, silicon. It excites electrons, creating an electric current. So this technology powers everything from calculators to large-scale solar power plants. And next is the photomultiplier tube. So these are highly sensitive lights detector that amplify weak light signals. So it used in scientific instrument, medical imaging, and astronomy. They help detect extremely low levels of light. So they work by emitting electrons when struck by photons. So then multiplying these electrons to produce a stronger signal. And lastly is the night vision devices. So used in military, security, and wildlife observation. So these devices enhances visibility in low light conditions. So they work by detecting infrared or low intensity light, converting it into electrons and amplifying the signals to create a visible image. So these applications demonstrate how the photoelectric effect is crucial for various industries, from renewable energy to advanced imaging technologies. So the limitations and further implication of photoelectric effect, wave particle duality. So the photoelectric effect provided evidence that light behaves as both a wave and a particle. So traditionally, light was thought to be only a wave, but Einstein's explanation showed that light also behaves as discrete package of energy called photons. And then the impact on the photoelectric effect impact on quantum mechanics and particle physics. So the study of the photoelectric effect led to major advancement in quantum mechanics, which describe the behavior of particles at very small scales. So it helps shape modern particle physics, influencing theories about the nature of light matter. So in conclusion, light energy is quantized into photons. So instead of being a continuous wave, light consists of discrete energy packets called photons. So each photon carries energy proportional to its frequency. And electron emission depends on frequency, not intensity. The photoelectric effect only occurs if the light's frequency exceeds a threshold value. Increasing intensity of light frequency light does not cause electron emission. And Einstein's explanation revolutionized physics. His work challenged classical wave theories of light and laid the foundation of quantum mechanics. And that's all. Thank you.